homework and stuff. I posted homework 2. It's due on the 10th, which is a Friday, which is typical. So that gives you 2 rounds of time with Sean. Sean will have answers for you next week, maybe even sooner. You'll also notice there's some repeats from last year as well. So I've just changed some things, but some repeats. I was taught about a little bit about the exam. We're running a little more slowly than I had hoped, but that's not a bad thing. It's just that we've found more things to talk about than I thought I would. So we'll probably have that after spring break at some point in March. I think spring break starts after that. 3:10 is the last day of class, right? The next week is spring break. So that was at the 13th? Yeah, 13th. So I'll post a practice set of problems that week, probably actually before spring break, to get you ready for the take home. You can I think we're going to kind of take the take home as kind of a short-term problem set in some ways. I haven't really figured out how I want to do that. But it'll be out for like a week or 10 days or something like that. I'll probably have it come out on a Wednesday, and it'll be due the Friday after, the next Friday, not 2 days, but a week plus 2, 10 days. So I'll post a practice set of questions. The take home will be on the atom. We haven't started it yet, but by the time we get there, we'll be pretty deep on the atom. And of course, it will have the fundamentals as well. There's going to be some angular momentum and some postulate kind of work. Of course, you have to have those to talk about the atom, but I'll kind of focus around the atom in particular. So I'll have some practice problems for you to think about over the break. Yeah. Any questions about any of that? Okay. I want to spend one last day on angular momentum, and then starting on Monday we'll start the hydrogen atom. We'll be all ready. There's one kind of angular momentum I haven't talked about yet. That is essential for understanding, basically all of chemistry, the most important type of angular momentum, but one that's particularly important for the hydrogen atom, or really any atom. And it's this idea of spin. Right. And I want to kind of talk about spin in the context. Am I recording? Okay. I want to talk about spin in the context of how we've talked about diatomic spinning. We'll talk about what spin is and how the physics are similar, but it's an entirely different kind of world, spin, compared to the spinning of an object. But the math will be very similar to angular momentum, but the consequences are very different. And I want to first talk about how do I want to say this? Let's first talk about, let's just recap a little bit of angular momentum and then kind of transition into spin. And there was 2 points about angular momentum that we learned. One is that, we have wave functions and energies, but some other points, that maybe some more relevant ones, is that there are 2 relevant operators for angular momentum. One is L squared. Remember that we have the magnitude of the angular momentum squared, L squared. And when you apply that to psi, you get h bar squared, and then this j plus 1 term, this quantum number term, j is a number, times psi, right, where j can be any number between 0, 1, 2. Right? These correspond to these angular states. We often call these, in atomic physics or any other place, we call this S, P, and D. And so a system that has no angular momentum is an S state, right, like the 1s orbital of the hydrogen atom. You can correlate to the hydrogen atom here. You'll see that more often. And then there's one other operator, right, which tells us something about the direction of how the system is spinning with respect to some axis. I picked the z-axis. It's totally arbitrary, as we'll see in just a second. And when you apply that to your wave function of your spinning object, you get h bar times this quantum number m times psi, where m can be any number between minus j and j. Okay. Right, and so again, the reason why we call these the P, if J is 1, then M can be either -1, 0, or +1. That's 3. Of course, there are 3 P orbitals. And D has 5, and so on. So there are 2J plus 1 M states. Okay. Right? Or there are 2J plus 1 orbitals for each angular minimum state. We'll see that in hydrogen atom. All right, and so this kind of tells us everything that we need to know. Everything is defined with respect to these two numbers, right? The weight, if you remember, for a diatomic, the energies are dependent on J, and the wave functions are dependent on both quantum numbers, which are these spherical harmonics, which we call Y. And they're just wave functions that are dependent on the angles of rotation. Okay, so we've seen these come up, right? These are your orbitals, and this is your energies. We're going to see this structure again in the hydrogen atom in a little different way. But in general, these two equations tell you everything we can understand about angular minimum. These are the only two things that we can know. We can know that basically the magnitude, how fast it's spinning, and the direction at which it's spinning in the long one axis. Now there's a particular question is why do we not, for instance, why am I not writing the other two components here, x and y? Right? After all, L is a vector. It has 3 directions in 3D space. But I've only written one. And in fact, I can only write one. And in order to explain that, I need to give us a new tool that will actually be able to kind of show why this is the case. The tool I want to introduce is called the commutator. All right, and I need to set up the problem a little bit so we can analyze it. Set up what a commutator is. So bear with me. Let's do a little setup. Let's assume we have some Hamiltonian, right? Some energy operate H bar, such that we can solve the Schrodinger equation, H psi equals E psi, to get a set of orthonormal wave functions, right? Those are our orthogonal wave functions that are normalized to 0. All right, I'm going to make them a set, which is those curly brackets, put psi n in there, right? That's our set of wave functions, all the different states of our system. And a corresponding set of energies. P sub n. Okay, so there's a set of wave functions, infinite ones, right? Should be an infinity, it's an infinitely large set, but countable. We can count them 0, 1, 2, 3, 4, 5, but there should be infinite of them, and there's an energy corresponding to each one. Right? You apply the Hamiltonian to it, get the energy back. Okay, so we have a nice set of wave functions. Now what I want to do is I want to measure another property. Okay, so we've measured energy here, but maybe we want to measure another property of some sort. So let's assume we want to measure 2 observables. Well, let's just say another observable. Not 2, but just another one. And let's say it has an operator A hat. All right, so we apply A hat to psi n, and we get some number A sub n times the wave function back, right? Just like before. Okay. I'm going to get rid of these n's real quick, though. All right, let's just say that's satisfied for some set of wave functions. Let the wave functions satisfying the equation for A be called, let's just give them a name. Instead of psi, let's give them phi instead. Okay, so you have a set of equations that satisfy the Schrodinger equation. Maybe we want to look at another observable A, and I'll just write here A phi is equal to phi, right? I've just changed their name just to have them different. We don't know if they're the same wave functions, if psi and phi are the same ones, just that we have two operators and there's a set of wave functions associated with them. And the question is psi and phi the same? Okay, do we need to specify two different perspectives on our system to get two different answers, or can we get two different answers from the same set of equations? You'll see where this comes in just a minute. There's a way we can calculate it. In order to calculate this, we compute what's called the commutator. Okay, so for this example, the commutator is written with brackets, and inside the brackets are the two operators we want to consider. So in this case, in our example, we have H and A. Okay, so this is what we call a commutator. I'll actually write out the formula for it in a second. But anytime you see two operators within these square brackets in this class, we'll see them occasionally, then commutator. All right, and the commutator is just a new operator, which is applying A, then H, and then subtracting the difference where you swap the measurement. So let me explain what I mean by that. So imagine now, write this out. Now what I'm going to do is these are just operators, right? So this is a difference of operators. So this is an operator itself. So what happens if I apply it to psi? Well, then I get H, A, H, psi. And then I can distribute the psi out. So you get HA psi minus AH psi. And the important thing to note is that with operators, you apply the right one first to the wave function, then the next one. So we apply this one first, right? We ask the question A to it, and then that result we apply H to it and ask that question. And then look at the difference here. How does this change? Well, here I'm applying H first, and then I'm measuring A second. Okay, so what I'm doing here is I'm measuring two things simultaneously. All right, I'm measuring A first, whatever that is. It could be position, momentum, angular momentum, whatever you want. I measure that first, then I measure the energy. Okay, I ask one question, then I ask the next question next. And then I subtract from that result. This should give me a number. I subtract from that the number that I get when I ask the energy, and then ask for the other one. Right, so I'm just swapping the orders of the questions that I'm asking my system, and I'm subtracting the difference. I'm calculating the difference between the two. And there are two results. If this is 0, okay, which means that I get the same result regardless of the way that I ask them. Okay, so I get the same result no matter what. Then theta and phi are the same set of wave functions up to a transformation. All right, so they represent the same object. Right, they might look a little different, but effectively they're the same. Maybe I have to rotate them a little bit to get from one to the other, but they're the equivalent. Right, so what that means is that if I set up a system to solve for A, and the commutator of A with H is 0, then that means that I can also write H phi is equal to E phi, and that will also work. Right? That's, theta and phi are effectively the same thing. Right? That we can simultaneously define a state for both observables. However, if it's not equal to 0, then theta and phi are mutually exclusive, and do not exist simultaneously. What this means is this means that when I solve the Schrodinger equation to get a set of wave functions, there's only so much information I can learn from it. Right? There could potentially be other questions I can ask that give me a non-meaningful result when I measure them with something I can measure. Let me show you an example of this. Back from the homework. So let me, for instance, ask the question, and you can evaluate these using a little bit of algebra, but I'm just going to give the results. So example is, what if I look at the commutator between energy and position? So I have a set of wave functions that are defined in terms of their energies. Are they also defined in terms of their position? And it turns out that this is 0. And this should be obvious because when we solve h psi equals e psi, we get wave functions that are defined in terms of position. Right? So that means we can talk about their position and their energy simultaneously. So these are wave functions with well-defined positions. Okay? So we can talk about position and energy simultaneously. Right? We can have one set of functions that describe our system that allow us to ask questions about both position and energy simultaneously. Another example, which we don't see that much in this class because we don't really do much momentum work in this class, but if you change x with p, this also works. Right? We can easily solve the Schrodinger equation for a set of wave functions that are defined in terms of momentum instead of position. Right? We can have the variable be momentum instead of position. We don't do that in this class, but it turns out that you can do either. You can have a choice. But now the question stands, what about x and p? Oops, sorry. What if I have a system that's defined in terms of position? Can I ask it questions about momentum and get a reasonable answer back, a meaningful answer? And the answer is no. Because when you do this, you get IH bar. What this means is that a wave function defined with respect to position is undefined in momentum. Okay? And vice versa. Right? If I were to write instead p hat x hat, I get minus IH bar. Right? So you saw this in problem set 1. Problem set 1, I had you look at this idea of defining a wave function in terms of a specific position, and I asked you, how do you represent a wave function in momentum? And you find that you have to have infinite momentum to define an exact point, and vice versa. If you have a well-defined momentum or wavelength, then your position is undetermined, and vice versa, right? And that's explicitly encoded into here. The fact that this does not give back 0 tells me that that has to happen. All right, it's just this number itself doesn't have a lot of meaning necessarily. You can actually get some physical meaning from it. But it tells me is that if I define a system in terms of its position, I can't know its momentum, and vice versa. All right, by definition. Why it's complex is quite interesting. The idea is that if you have a position that's specific to it for point x, okay, so here's my wave function in terms of x. Right, it's a defined position, it's right there. Right, this is equivalent to a system processing around a circle with a complex value. So it's a circle instead. So when you see I, this usually means undefined and has an oscillatory behavior. So you can actually write, so what happens is that if you have a real position, then your momentum is imaginary. And when you have an oscillating system, an imaginary coordinate means it's moving around in a circle, right? So position is basically the momentum of your system is sampling all possible momentum in a circle, of all possible values in this circle, while your position is exactly defined. Likewise, if you define a specific momentum or wavelength, then your system is oscillating between all possible values of the position. Right? It's just going in a circle in time around them. Right? So that's what this I means. Right? So when you see I, you can think of it oscillatory behavior. The idea is that if you have a fixed position, then you have an oscillating behavior in the other coordinate. All right, this leads to a very, very, very important property of position and momentum, which you kind of looked at on the homework, and I kind of mentioned it. But it's this idea of the Heisenberg uncertainty principle, which says that the error in your position and your momentum is always greater than h bar over 2. Right? And it turns out, right, so this means that if you're well defined in position, then your momentum is infinite, and momentum definition is infinite, right? This is the error in position, and this is the error in momentum. So if one goes down, the other one has to go up because they're all bound by h bar over 2. Okay, and this actually comes from this. What you can show is that the uncertainty in two variables a and b is always bound kind of proportionally, roughly, by 1/4 the square root of the average value. Let me write this down properly, of the commutator. Something like that. I forget exactly what it is. But so again, your commutator has this value IH bar, and then the error in that has some proportionality to, sorry, this is not squared. Proportionality, so you're going to put some IH bar inside of here, and it ends up coming out the IH bar squared. I think I've missed a square somewhere. It might be a square in there. But anyway, the point is that the uncertainty in two variables that you have, say, momentum and position, is defined based on its commutator value. So for instance, if I were to write if we have an error in energy versus position, right? If I want to multiply my error in my measurement in energy times my error in position, or calculate one versus the other, well, it is equal to 0 because its commutator is 0. So this thing goes away. Right? So for instance, delta x, delta E is 0, right? And delta P, delta E is 0, right? So you can actually, what this means is that you can determine energy and position precisely together. You can measure them simultaneously to whatever precision you can do, or momentum and energy together. You can measure them both at the same time. But momentum and position you can't, right? It's fixed. Right? So the better you measure one, the worse you know the other. Okay, so now I've kind of gotten off to the side. Now the question is, what does this have to do with angular momentum? And all we have to do now is remember that in angular momentum, we have two operators that we care about, L squared and LZ. All right, so maybe we should ask the question, L squared, LZ, the commutator of these, right? If we can define our wave function in terms of L squared, which is what we do, remember that the energy of a rotating system is L squared over 2I, so they're proportional to each other. So this is basically asking the same as H and LZ. And this is 0. Of course it has to be 0, right? Because we've defined our system. I don't have it up on the board anymore. When we talk about a rotating diatomic, our system is defined in terms of M and J. Right? Our wave functions are dependent on both of these variables, or the measurables of these two, right? M and J. So of course the commutator has to be 0 because our entire system is defined with regards to these two. But the thing is that our choice of of z is arbitrary because I can measure the direction of the angular minimum along any direction I want. So I can write L squared LZ, L squared LX, L squared Ly, and these are all equal to 0. Right? I can define my system in terms of any of these three axes. As long as I have L squared, as long as I know the magnitude of the vector, and one of the directions, I can define a system in terms of that. Right? So what this means is that there is a set of wave functions that allow simultaneous observation of L squared and LZ. Okay, right. So what the kind of take-home point of this, in some ways, is that the commutator tells us what information that our wave function can return. Right? It's only defined in terms of a specific set of coordinates. And in angular momentum, our wave function is defined based on the length of the vector, L squared, and its projection along one of the axes, the z-axis in this case. But it's just an arbitrary choice. But I can choose any of the three axes, and it's totally okay. Right? I don't know if you prefer X or you prefer Y, you can certainly enjoy them. But there's really no reason to pick one or the other. Just typically we pick Z. Okay, so, but what I said is that we can only pick one of them. We can't pick two, right? So I can't define a wave function that has well-defined meaning along two axes and its length. Right? And the way to show this, turns out, is to calculate, for instance, the commutator between LZ and LX. So if I have a wave function that's defined in LZ, is it also defined in LX? And when you calculate this is a part of homework 2, you get the other operator out for the other axis. So when you measure LZ and LX, when you measure these two simultaneously and then flip it and measure them simultaneously in the opposite direction, your difference is by a rotation around the y-axis. Right? Your system is now undefined completely. Right? What this means is that you've measured these two, and now you've lost all meaning because now you return something along another y-axis. Right? So I'm asking a question about the z and the x-axis, and I get a question about an answer about the y-axis back. Right? Which means that these are not well defined. Right? And I could write the same thing. I could write Lx, Ly, and I get Lz back. And then if I write, what's the one I'm missing? Ly, Lz, I get Lx back. Okay, so what this means is that when I create a system, when I describe the angular minimum of the system, I can know its length, I can know one projection, but I can only know one projection. Right? If I make a measurement across two different axes of my system, I get an answer about the third. Right? Which means that these are not defined. Or rather, maybe a way to think about this is when you measure these simultaneously and then flip your question so that you measure them simultaneously in the opposite way, you do something to your x-axis, right? You manipulate your system. Right? So what this is now difference in LZ, LX minus LX, LZ is a manipulation along the third axis, the y-axis. All right, so what that means is that when I take Ly, Lz, I measure those together, and then I take Lz, Ly, the system is different by some value on the other axis, right? I've changed the state of my system. All right, so this means that I can't make these measurements simultaneously without affecting my system, right? Which is not what we want. We want to be able to ask the wave function questions and get results back without changing anything about the state that it's in. But what this is saying that if I'm going to measure the projection of the axis along two different axes, or projection of the angular minimum along two different axes, then I'm going to manipulate the system so that it changes it along the third. All right, and that's no good. That means that I've caused a manipulation to my system. Right? I've perturbed it, and that's no good. Right? We can't learn anything from that. It turns out that this has very, very profound consequences. And the way I want to describe that, it's very hard to see it here, all right? Because it's very hard to think about how angular momentum is changing for an object that's just floating in space. So I want to simplify the model a little bit. And that'll bring us to spin. Right? I'm going to use all of these rules now, and I'm going to apply it to this magical type of angular momentum called spin. Right? And what is spin? Well, spin is spin. Unfortunately, there's not really a better way to explain it, but rather, oh, that's a bad marker. I got to change that one. Spin is the intrinsic angular momentum found in all but one fundamental particle. Right? There's many different particles in the world, fundamental particles. There's the electron, right? There are quarks. We can even think about protons and neutrons. They're not fundamental. They're composite particles, but they all have spin. Right? They have some intrinsic angular momentum to them. And there's only one that doesn't. That's the Higgs boson. It has spin 0. It's the only one that doesn't. We don't have to worry about that at all. What we could say is that all particles have spin, and that would be reasonable, because we don't care about the Higgs boson. That's a very weakly contributing, doesn't exist in chemistry at all. So everything has this intrinsic angular momentum, right? And we can often write, so for instance, we talked about this before, the electron is spin, we call 1/2. All right, we'll talk about what that means in a second. The proton has spin 1/2, and the neutron has spin 1/2. What this means is that the electron and the proton, no matter what state you find them in, right, what energy, doesn't matter. There's this intrinsic spin that they have, this angular momentum. They're always spinning with respect to an axis, right? You can't get rid of it. And the math to describe these is precisely the same as the math that we describe angular momentum. So what I can do is define a spin quantum number S. Okay, and so in the case of the electron, S is 1/2. Right, it's a half integer number. And we could define two operators, S squared and SC, right? This is an angular momentum, so we can measure a vector, right? We can measure we can measure a component of it and the magnitude of it. And we have some wave function. And this returns the exact same formula as angular momentum, S times S plus 1. Right, we've just changed the label. And SC is h bar, and it returns this number m sub s. Okay? And so S is, but remember in angular momentum, for like a diatomic J, which is S in this case, can be any number, right? But here, S can only be one value. Right? Electron has a fixed angular momentum. It can't have any other. The spin is always a fixed number. Right? So instead of having a spectrum of values, we only have one quantum number. Right? So let me erase this. So S here is 1/2. So that means S squared, right? Just plug it in, is h bar squared 1/2 plus 3/2. So that's 3h bar over 4. Right? And S, remember, m sub s can be anywhere between minus s plus 1, s minus 1, s. But s is 1/2. So the only values that m sub s can be is minus 1/2 and 1/2. Right? Negative s is minus 1/2, and you add 1 and you get 1/2, and that's it. Right? That's s. These are only two values. So electron, or proton or neutron, they're all the same, has only two spin angular momentum states. One we call 1/2 and one we call minus 1/2, right? We can call, so one is m sub s equals 1/2. We often call that the up state, right? I'll draw an up arrow for that. Different labels. One is the up arrow, and another one is alpha. We'll call it alpha later on when we talk about molecules. And then the other one is where it's negative 1/2. We call that the down spin, a down sign, and sometimes we'll write it as beta. Right? Different labels for the same thing. Okay, so we've really simplified our spectrum, right? We only have two states, right? Instead of a molecule, or diatomic molecule rotating, that has an infinite number of states, right? J can be any number. But the spin is fixed, so it can only have two values, two projections. But notice, sorry, and so this is S. C is 1/2 plus or minus 1/2 h bar over 2. Okay, so the interesting thing here is that once again, we can only measure Z. We can't measure X or Y, right? So the same things apply. If we measured the spin axis along different axes, we get IH bar times the other one, and so on and so forth, right? So spin, just like angular minimum, is only defined along one direction and a magnitude. Right? So these only one component component is defined. Okay, and so you can, turns out, so what that means is that here's the really neat thing about things with spin. So for instance, electron. All right, an electron is just a point-like particle, no shape, thus has no electric dipole, right? It's just a -1 charge, so there's no charge distribution, right? So it's just a -1 charge floating in space. Okay, so what this means is that to electricity, the electron is a formless point charge. Right, so when you put an electron in an electric field, it just floats around like a negative charge. It doesn't do anything very interesting. However, if you put it in a magnetic field, the electron, so I'm going to put the magnetic field along the z-axis. So here I'm going to draw a ball of charge here. This is our electron. Here's my z-axis. I'm going to apply a magnetic field along this direction. All right, so there's my magnetic field being applied for that direction, so we can have like a negative magnetic charge dipole here and a positive one here. Right, so the magnetic field's going to go this way. But this electron has an angular momentum component that's not 0, S. Right? And it has a projection along this axis of 1/2 h bar. So what happens is that when you put this point mass in a magnetic field, it acts as if it were a particle with some object attached to it spinning around. So in terms of a magnetic field, you have a negative charge here and kind of a positive magnetic charge there. It acts like a diatomic molecule, the spin, right? Because you have an angular momentum component. And so when you excite, or when you put an electron in a magnetic field, it rotates and precesses like it has an object, like it has a shape. Right, so this thing will start to rotate. Right, this is the origin of that spin. Right, this is why we call it angular momentum. It's because in an electric field, we put an electron in there, it just acts like a ball of charge. It just floats around and doesn't do anything interesting. But the moment you put it in a magnetic field, because of the spin angular momentum, the system actually has a magnetic dipole moment. So there's a magnetic distribution of charge in the electron that's negative to positive. And when that interacts with a magnetic field, it rotates. It precesses. The atom precesses, or the electron precesses. Right? So electrons, so things with spin are inherently magnetic. Spin leads to a magnetic dipole moment. So interestingly, the electron does not have a shape around an electric field, but the moment you put it in a magnetic field, it acts like it does. Now, it doesn't have a real shape. If it had a real shape, it would have an infinite number of angular momentum states, right? You could excite it to go faster and faster and faster, right? If it were a diatomic or like an electron, if you had something actually rotating, right? But in spin, we only have one state. There's only one half. There's the plus one half, and then there's the minus one half component, right? There's only two states, plus one half and minus one half. So the electron isn't a real rotor, a rotor in a magnetic field, but rather it acts like a rotor, but it only has two states, right? It can't change its angular momentum. It just has angular momentum, constant angular momentum. Okay, so that's really cool. Electron kind of acts like it's a physical object when you put it in a magnetic field. We can do some really cool stuff with this. Let me show you an example of that. What I'm going to do is do an experiment. This is called the Stern-Gerlach experiment after Otto Stern and Gerlach, whose first name I don't remember. What I'm going to do is I'm going to shoot some spin one-half particles. It could be electrons. It could be they use silver atoms traditionally. But something with a spin of one half, and I'm going to pass it through a magnetic field and make some measurements of it. So what Stern and Gerlach did is they created an oven or a gun. It's a really bad gun. That shoots out silver atoms. All right, so these are silver atoms. This is an AG atom gun. All right, so that shoots out silver atoms. Silver atoms have one unpaired electron in their valence shell. Has an electronic spin, neutral silver of one half. All right, it's got one unpaired electron in its valence shell. It's 4s1. So its total electronic spin is one half. Right, so it acts like an electron. The spin angular momentum of silver has the same physics of an electron. So what I'm going to do is I'm going to shoot these atom guns out. I'm going to shoot this stream of atoms out. Maybe it spreads. There's a lot of them. And then what I'm going to do is I'm going to filter out some of the atoms to make a nice narrow beam of atoms. And so I just kind of bubble through some silver atoms and get a nice straight line. Right, so I'm going to collimate them. Collimated beam. And then what I'm going to do is I'm going to pass them through a magnetic field. So what I'm going to do is I'm going to draw a magnetic field, a box here that magnetizes our field. And I'm going to magnetize them along the z-axis. So let me draw my axis system here for you. So z is up and down the board. We'll say x is across the board like this, and y is in and out of the board. Okay. So the board is the xz plane. And so what I'm going to do is I'm going to magnetize them along the z-axis, right? So I'm going to put a magnet that magnetizes them up and down the board. Okay? It's not going to deflect them in and out of the board, just up and down the board. Okay, and I'm going to make this a crappy magnetic field. So we call it an homogeneous magnetic field, which means that what that means is that the strength of the magnetic field varies with position. There are going to be regions that are more magnetized than others. And so what happens is that if these were normal magnetic particles, magnetic field, if one comes in, it might go out this way, it might go out this way. One might bounce around like this and fly out, right? They can just go random directions along the board. Okay, so it randomly ejects silver atoms on the other side. Okay, these silver atoms are spin 1/2, so they're magnetic. They magnetize fairly well. And if they were just classical balls, right, balls of charge, they'll go through here and get randomly magnetized, and then they'll get shot off into random directions along the board. Okay, and I want to measure that, right? I want to measure the distribution of my charges, or my atoms as they come out of the system. So here I have a detector. Okay, and I'm going to image the silver atoms as they attack the board, as they collide with the board. And the question is what do I observe? All right, so I'm going to draw I'm going to draw a prediction and then the result. All right, so if we ask classically, these are just point charges moving randomly. Right? Think of it as an ideal gas of magnetic particles. We move them through a magnetic field that's randomized. They're moving at random velocities, random directions. We get randomized. What do we expect? Well, there's no preference. There's no preference for them to get deflected down the board or up the board. So on average, they're not going to get deflected at all. There's going to be some on the wings, but it should be symmetric. Right? So classically, we would expect to see very few on the edges. And then as we get close to the center, it peaks. And then it's symmetric across the other way. Right? We would expect to see them kind of bounce around randomly, and you just get a standard distribution. Now, what do you see experimentally? Well, here's the thing. Our electron, or our silver atom, has two angular minimum states. There's one that's basically positive, right? It reacts with the field. Right here, it's moving with the field, and here it's moving against the field, the negative state. And our atom should be 50-50 plus or minus. There's no preference for them to be. Right? So these are 50%. I'll just write that here. They're 50% spin up and 50% spin down. There's no preference for one or the other. But when you apply a field, there's going to be some of them are pointing this direction with the field, and some are against the field. And what that means is that some are going to deflect this way, and some are going to deflect this way, against the field and with the field. But there's only two options, right? There's only two angular minimum. There's only two magnetic states, right? The system can only be deflected in possible two states, two spin states. So in fact, what we see experimentally is a bimodal distribution like that, where this is corresponding to the -1/2 h-bar state, and this other peak is the +1/2 h-bar state. Right? The system doesn't, on average, magnetize. Right? This would imply that on average the magnetic effect is 0 because the deviation negative and deviation positive are equal and opposite to each other because it's all random. But what we actually have is that the electron or the silver atom can't be 0 magnetism. They're all magnetically aligned, either positive or with the field or against the field. There's nothing in between. So when the electrons get deflected, half of them go here, and half of them go here, right, corresponding to the two spin states of the silver atom. Right, this was a big deal when this happened because the idea of spin wasn't really proven at the time, and no one really could understand. This was done like the early 1900s. Why you get this bimodal distribution, and of course it became very clear very quickly that there has to be another angular minimum component that we're not accounting for that doesn't have a classical analog. Right? The only difference between these two observations, in fact, is spin. If the system didn't have spin, then you would get the classical result. Right? But when you add spin, you get a completely different distribution. You get this bimodal distribution, right? Because they correspond to these two spin states of the atom. We can do really, really cool things with this. Now what I'm going to do is I'm going to do a super Gerlach experiment. So here's my gun. I'm just going to draw it in terms of boxes now. All right, so I'm going to shoot my silver atoms through my slit. And then what I'm going to do is I'm going to pass it through a Z box that magnetizes it along the box. And we know that when you do this, your atoms get split into two groups, right? It gets the plus group and the minus group. This is the -1/2 h-bar. This is the +1/2 h-bar. Right, so what I'm going to do is I'm going to block one off. I'm going to filter out these atoms. Right, so the minus 1/2, these negative ones, I'm just going to block off. Right, this is a wall. I'm just going to get rid of them. Right, so I'm going to filter out all of the ones that are minus 1/2, right, all ones pointing the opposite direction against the field, and keep the positive ones. Okay, so I just filter it out. Now what I'm going to do is I'm going to take these atoms, and I'm going to run it through another Z box. Like so. Okay, notice that what I've done here is I've made a measurement of SC here. Right? I've measured, right, the result is either plus 1/2 or minus 1/2 H bar. So I've made this is basically applying an operator, the Z operator, the projection operator. And I'm going to do it again. Right? But we already know the result of these. Right? SZ for these return 1/2 H bar. Right? So we have these positive 1/2 H bar, positive 1/2 spin silver atoms coming into here, and we're asking the question, what's your spin? Well, there's only one answer. We're going to get 100% out that are plus 1/2. And then I'm just going to write this 0%, minus 1/2 H bar. Right? Because we've already identified them as being positive 1/2, right? To spin up. So everything that comes through here is spin 1/2. So you get 100% out. These are 50-50, of course. First measurement is 50-50. Okay, so now what I want to do is so all I've done here is just a sanity check. Right, I've done the same thing twice and I get the obvious result. Everything that gets filtered out is 100% that. It doesn't change. There's nothing wrong with me making the same measurement twice. You can show that the commutator between SE and SE is 0. It's obvious once you work out the math. But what I'm going to do now is I'm going to magnetize across a different direction. Let's go to the Y. Right, so now what I'm going to do is I'm going to magnetize the system in and out of the board. Right, so this is kind of rotated 90 degrees relative to Z. So what's going to happen now is I'm magnetizing along the Y-axis. So depending on the values of the spin, some are going to go out of the board, some are going to go into the board. And when you do this measurement, what you find is 50% come out minus 1/2. And once again, 50% come out plus 1/2. It's lost its information. Right? Notice that the projection along the Z-axis here is 1/2. Right? It's 1/2 here. We're all good. And then the moment I hit Y, the system is now mixed up again. But that's okay. We've said that we've defined the axis, the Z-axis projection. We know how it's directed along the Z-axis. Well, that doesn't mean that it's 50-50 Y mixture, right? Just because it's pointing this way doesn't mean it's pointing this way or this way. They're still 50-50. Right? So that's okay. All right, so what I'm going to do is I'm going to do the same process again. I'm going to block off the minus 1/2 H bars. And I'm going to feed these through again, the plus 1/2s. And I'm going to put them back into a Z box. I'm going to ask the same question again. So again, this is S sub Y. And I'm going to run them through my Z box again to measure the Z component of the spin. And lo and behold, I've lost all information. This splits up 1/2 again. Half and half. Now let's walk through this again. I've filtered out all the ones along the Z-axis that are positive. I've confirmed that that's the case. I've now measured their component along a different axis. Okay. And again, so if these look like vectors like this, then we've had just these. And now what I'm looking at are ones that are pointed. Let me see if I can do this. Pointed out of the board along the Y-axis, and ones that are pointed into the board along the Y-axis. So the Y again, just as a reminder. Right, so just because it's pointing this way doesn't mean it's this way or this way. Right, so that's fine. But the moment I go back and I make another measurement of the z, I've lost all my information again. Magically, my plus 1/2 spin, or the ones pointing this way, after I've measured y, have gone back to either being plus or minus. Right? We have lost all information. And they're randomized again. This is what's happened. This is the point of these commutators. Right? Remember that. So the first, if we think about these measurements, the first two measurements, we're measuring SZ, SZ. Of course, this is 0. Right? So that means that the wave function for the system is defined well against the z-axis, and you're still defined along the z-axis here. But now I've switched to the y-axis, and we know if I take the commutator of the spin operators along the s and the z-axis, I get a non-zero value at s of x. Right? And so what I've done now is I've taken a system that's represented in terms of z, and now I'm making a measurement in terms of y, and y and z are not correlated. They're not simultaneously identifiable. YZ, the set of YZ functions is not equal to the set of functions defined along the y-axis. They're completely different. So what I'm doing is I'm making measurements. Making measurements of the same system. Of course, they're the same atoms. But I can only ask specific questions in my interpretation. My questions can only be asked from the perspective of the z-axis. And the moment that I switch to a different axis system, right, I'm now changing my perspective to the y-axis. I've lost all information about the z-axis because I've thrown away that data. Right? I've gotten rid of, basically by localizing the system along the y-axis, I've delocalized it on the z-axis. And so when I take these back and ask it for z, I've done that conversion again. I've now taken a system that's defined in terms of the y-axis, and now I'm measuring it in terms of an undefined axis, the z-axis. So I've lost all that information. Okay? And you can do this, people have done this process, they have chains of them, of these magnetic boxes. They'll even set them up on rotating things so you can rotate to, right, you can have your magnetic field halfway between x and y if you want like a 45-degree angle. And the distributions of the spins that come out of them correlate with those angles. You can imagine that if this were SZ instead of SY, so if this were SZ, I would still get 100% out. And then what I can do is I rotate my Z magnet towards the Y. And as you do that, you'll start to see more of the other components start to appear. So for instance, if this were perfectly SZ, I'd get 100% out plus. And then as I start to get towards SY, by rotating the magnet towards the y-axis, I'm taking a Z magnet and rotating it like this, you lose some into plus and you gain some into minus. And then once you do that 90-degree rotation, it becomes 50-50 again. It's a smooth transition. Right? And so what I'm doing is I'm converting my system slowly from a perspective along the z-axis to one that's undefined in the z basis, now the y, and back to z again. Right? Wave functions, the point is that wave functions are not universal. They are defined with respect only to variables that commute. Okay? If the two variables don't commute, x and y in this case, then the system falls apart, right? It's undefined in both one of the, you can only choose one. Right? And that it physically happens. Here I'm choosing z, I transform to y, I lose my information, I transform back to z, and I've lost all that information I had before. So there's always some indeterminacy. There's nothing you can do about this. Right? And again, that's why they started rotating it. They're like, well, if I'm halfway between y and z, then maybe it doesn't happen until I do a full 90-degree rotation. Right? That these measurements work if the magnet is just slightly tilted towards the y-axis, but mostly z. But in fact, that's not what happens. You get a smooth transition. SZ will become increasingly less and less defined as your magnet rotates towards the y-axis instead of the z-axis. There's nothing you can do about it. You can't get around it. Okay? How much time do I have left? 15 minutes. Great. Great. I want to show one more thing about this experiment. You've seen this before. If you've done organic chemistry, you've done spectroscopy, you've seen this before, but we have to make one small change. What I'm going to do now, this was done by a man named Isidore Rabi. He saw this experiment with the spins and said, well, what if I try something a little different? So he has a silver gun. He's going to shoot his particles out, and he's going to put them through a Z-magnet. But he's going to do something slightly different. Instead of applying a constant voltage, so this is plus and this is minus, he's going to apply an alternating current to it. So what the sign of the magnetic field changes in time. So for instance, I'll just draw it as a sine wave. That sometimes it's positive, sometimes it's negative, and sometimes it's positive. And what we'll do is we'll set the other one to be equal and opposite. Okay, so we're going to alternate the magnetic field in time at some frequency. All right, so this has some wavelength, right, at which the magnetic field resonates at, and the length of the box, we'll say, is L. And so let's say he sets the length and the wavelength at some value, right? And makes a measurement of the distribution of plus and minus. Okay? And so maybe he does this experiment, and on this detector, we'll say at L equals 1 and lambda equals 1. Just random values, for instance. And he sees, okay, there's a little bit of minus 1/2 and a little bit of plus 1/2. Let me make this go to 0. This is minus 1/2, plus 1/2. And let's say it's 50-50, okay? All right. And then what he's going to do is he's going to do the same thing, same experiment, but he's going to double the length of the magnet, right? He has to go through a magnet twice, but at the same wavelength. And he's going to do the same experiment. And what he might find, in fact, is that it's not 50-50 anymore. Maybe it's 66-33. And then he's going to lengthen it even more, triple the length. I don't know what it is, but just as an example. These numbers aren't quantitative, just as an example. He only gets one out. Get this nice and stable like that. There we go. And then he keeps going, and what he finds is that as this oscillates towards 1/2 h, and he keeps getting longer and longer, that it goes back, and then eventually everything's in a minus state. Right? And then he tries by increasing the wavelength instead, he sees the same result. So let's actually ask the question, what is the difference between the number of particles that are 1/2 that are measured as a function of the length, minus the number that are measured at minus 1/2 as a function of the length, and calculate the difference, the population difference. We'll call this the population difference. All right, so as he varies the length, he's going to measure a difference between the populations. Here it's 0, here it's 33%, here it's 100%, or undefined. All right, and then what Rabi does is he changes the wavelength or the frequency of the radiation, or changes the length that's equivalent, and he plots as a function of length, or wavelength, however you want to think about it, this population difference. Okay, what does he find? Well, he finds that at L equals 0, the population difference is 0 because there's no magnetic field, and so they're 50-50. And then as it increases, there is the absolute value. It goes up to some value, and then decreases again. Goes up to some value, and decreases again. Goes up to some value, and decreases again, like that. And what do we interpret these values as? Well, this value is where, this is 1 effectively, 100%. This is where everything is plus 1/2. And this is where everything is minus 1/2. And this is where everything is plus 1/2. It oscillates. Right? So as a function of time, the system oscillates between being 100% in one state and 100% in the other, and 50-50 in the middle. And it turns out that this wavelength the wavelength of this in terms of length is the same as the wavelength of the oscillating frequency. So what happens is that the system, these magnetic dipoles of your atoms or your electrons or your photons, whatever you want to think about them as, oscillates in time with this magnetic field oscillating time. And so what you're doing is you're taking an object that has a magnetic dipole. It's got some interaction with the electric field or the magnetic field. And it's oscillating between two states like this. It's going plus 1/2, minus 1/2, plus 1/2, minus 1/2. So you have an oscillating magnetic dipole that's going from like this to like this. And so if you can think about it, it's kind of the wave is kind of precessing along this axis like this. It's actually precessing at 360 degrees. The system is going up and down, up and down, and up and down. When this happens, Maxwell's equations say, electromagnetic equations say, emit photons. All right, when the system oscillates, a dipole oscillates with a field, it emits light. So what he does, in fact, is what he notices that when he does this, again, he can detect the ions and their spins, or the atoms and their spins on the detector, but if he had a photomultiplier tube sitting here as well, what he would find, oh, that's not where they're coming from. The waves are coming from here. What he would find in time versus intensity is an oscillating field. This is light emission. So what Robbie discovers is that if you apply an oscillating magnetic field to a set of spins, they smoothly move between their spin states in an oscillatory fashion, which causes an emission of light. Right? And he calls this a very specific term. He calls this magnetic resonance. Each atom has its own resonance frequency. Depending on the strength of the magnetic field, it changes. But basically, you can set a wavelength so that your spins will oscillate in time with the light, the driving light, and they're resonant with it. They oscillate back and forth in a resonant fashion with that light, or the oscillating field in this case, right? So Isidore Rabi did this with electrons at first, or with atoms with electrons, but they later realized that you can do this with protons too. The protons don't couple as strongly to a magnetic field as an electron does, but it does work. And so if you do this for say a proton, like a hydrogen atom, we can add one more term. It's the same thing, nuclear magnetic resonance. Right? This is NMR. Right? So NMR solely exists due to the fact that we don't understand, because of this issue with, or this commutation, this relationship between the angular minimum components. If we didn't have this, you wouldn't have NMR. In NMR, you drive your system along the z-axis, and in fact, NMR is a two-dimensional you actually do two measurements. So you drive the system, you polarize the system in the z-axis in this way, and then you spin it up along the x-axis. And when you're taking a measurement along two axes that aren't well defined, the system, when it does that, is it oscillates. And it goes between the upper state and the lower state along the z-axis in this way that the Isgor-Rabi does, but we apply a torque to the atom along the x-axis, and that causes the z-axis to spin. And that spinning is what we detect in a mark. Okay, so there's an extra step for NMR, but this is what you're doing is this exact same process, but you're doing along two axes. So you have one, you're applying an alternating electric field this way and one this way as well. And that causes the system to basically process along an axis and rotate along an axis, or have spin around it, and it emits light. Right? And that's how we detect NMR. So, all right, so if we knew all of the positions, if we knew all of the directions of angular minimum, right? If we could define everything, there would be no NMR. You would just spin the system up, and I guess technically you could maybe measure something, but the point of the matter is that NMR exists solely because you can only measure one component of the spin at a time, that there's only two spin states per spin 1/2 particle. You don't have a continuum of them. You only have two, and that you can only define them along one of the axes at a time. Okay, so this is spin. So we'll come back a little bit more and look at it more carefully. Again, in the electron, spin's going to be extremely important because all hydrogen atom. So in the hydrogen atom, all you have is the proton and an electron. They're going to be spinning, the electron's going to be orbiting the proton. But on top of that, right, so you have this orbital motion. But we also have to consider that the electron itself is the top, right? It has some angular minimum itself. You can think of the electron as its own top. So you're building a top, a hydrogen atom, a spinning top, where the electron is processing around the proton like this in some way. But at the same time, the electron is also spinning itself because of its spin, right? And so you end up having two angular minimum. You have the spin and the orbital part, right? The big orbit of the electron around the proton and the electron spinning itself through its spin. And so these can couple, they can affect each other. And that leads to very interesting effects in the hydrogen atom and many atoms, which we call spin-orbit coupling. These are the essences of magnetic fields, or magnetization. Right? If we didn't have spin like this, where it has unique discrete states and only a finite number of them, there would be no magnetic processes in the world at all. Right? So the entire concept of magnetization is dependent on this definition of spin. Right? You don't have spin, you don't have magnetization. So we need spin they're correlated, they're equivalent to each other effectively. Okay, so that's all I have for you today. So starting on Monday, we'll start the hydrogen atom. All right, we're basically 2/3 of the way through the hydrogen atom already. We have to talk a little bit more about the physics of electron around proton, just a little bit more. Well, we've already done the spinning part. Now we have to get the electrostatic attraction part as well, and we'll start that on Monday. All right, have a lovely weekend, everybody.
Stand hard up.
Yeah, take care.
Have a good day.
Me too.
See you soon.
See you soon.
Thank you.
Take care.
Experiment you started off.
Yeah. I put it at the beginning or later now.
Yeah.
Yeah, I kind
Just making sure I had things right.
of. No, you did. Yeah, I decided to put it later this time. Well, and we did harmonic oscillators almost immediately after particle in a box last year too. And as you know, we haven't even started